August 14, 1942. Detroit Tank Arsenal, Warren, Michigan. Plant manager John Carr's Cadden stood with a stopwatch in his hand, watching hull number 217 inch through assembly. The crews moved methodically, precisely, just as Army Ordnance specialists had trained them. Every motion followed the official technical manuals. Every weld met inspection standards. Every bolt was torqued to spec. The problem was time. Hull 217 had already sat on the floor for 11 days. It would take another 8 to complete, 19 days for a single M4 Sherman medium tank. At that rate, the largest tank factory in the world would produce roughly 420 tanks per year. The U.S. Army had ordered 10,000 just for 1943. At the current pace, Detroit Tank Arsenal would need 24 years to deliver a single year's order. The arithmetic of defeat was written across the shop floor in man-hours and assembly time, largely accepted by management as the inevitable cost of doing it right. A 47-year-old civilian production consultant named Charles Sorensen was doing math on the back of a requisition form. Sorensen had spent 36 years at Ford, revolutionizing automobile assembly with the moving line that turned the Model T into the first mass-produced car for the masses. He was conducting an unauthorized time and motion study of tank building. What he saw violated every principle of efficient production he'd forged across his career. The tanks were being built like custom machinery, with craftsman production applied to industrial warfare, crews swarming around static hulls to install components. It was impossibly slow. Sorensen's calculations suggested that with true flow manufacturing, the build time could be cut from 19 days to 48 hours. His colleagues thought he was crazy. Army Ordnance officers insisted it was impossible. Tanks, they declared, were not automobiles. Their complexity, precision demands, and specialized components required the cautious, stepwise approach then in use. Sorensen was about to prove them wrong. His impossible play applying continuous flow assembly to tank manufacture would yank American armored vehicle building from artisan craft into industrial mass production. Within 18 months, Detroit Tank Arsenal would run 24/7 and complete one Sherman every 60 minutes. This is the story of a civilian's manufacturing revolution that helped unleash the armored avalanche that smothered the Wehrmacht under American steel. The crisis began in June 1941, 6 months before Pearl Harbor. Watching German panzer divisions storm across Europe, the U.S. Army admitted American armor was outclassed. The M3 Lee, America's frontline medium tank, was already inferior to German designs. A new tank was needed, fast, and in quantities that seemed impossible. The M4 Sherman medium tank was designed in an astonishing 78 days, from April through June 1941. The design prioritized production over technical sophistication. The Wright R975 radial engine was already in mass production for aircraft. The 75 main gun used existing ammunition. The suspension adopted proven components. The hull was designed for welded construction to minimize the need for complex castings. Yet even with a production-friendly design, early manufacturing was agonizingly slow. Lima Locomotive Works won the first production contract in August 1941 and delivered the first completed tank in February 1942, 6 months per vehicle. By April, they were up to one tank per week. Still hopelessly inadequate, Detroit Tank Arsenal was supposed to be the answer, America's promise of mass tank production. Construction began in September 1941 on farmland in Warren, Michigan. The facility was designed as the largest tank factory on Earth. The main building has 1,600,000 square feet under a single roof. The assembly hall alone ran 1,200 feet long by 600 feet wide. Chrysler Corporation, having never built a tank, was contracted to operate it. The company brought automotive manufacturing savvy, but ran straight into institutional headwinds. Army Ordnance technical advisors insisted that tanks demanded fundamentally different methods than automobiles. Thick armor, specialized weapons, and heavy components, they said, mandated traditional stationary assembly. The first Sherman rolled out of Detroit Tank Arsenal on April 11, 1942, 7 months after construction began. First-month production totaled 12 tanks. May rose to 37. June hit 61. Progress, yes, but nowhere near the thousands per month Allied strategy required. The bottleneck wasn't worker skill, material supply, or equipment capacity. It was a method. Tanks were being assembled with techniques befitting custom locomotives, not mass-produced military equipment. Each hull sat static as teams worked through a long sequence of installs. Bottlenecks piled up. Workers waited for specialized tools for inspectors and for the prior operation to finish. Sorensen arrived at Detroit Tank Arsenal in July 1942 as a $1-a-year consultant. The title belied his reputation. Since 1906, he had been Henry Ford's right hand, helping turn Ford Motor Company into the world's largest auto manufacturer, and co-inventing the moving assembly line that slashed Model T build time from 12 hours to 93 minutes. He had stepped away from Ford in 1941 after clashes with Edsel Ford. But wartime idleness didn't suit a man who had emigrated from Denmark as a boy and made American industrial success his personal mission. When the War Production Board asked him to consult on tank manufacturing, he said yes immediately. His first week at the arsenal confirmed his worst fears. Tanks were being built with pre-1913 methods. Instead of the product moving past the workers moved around a stationary product. The difference seems subtle, but it is decisive for efficiency. Sorensen spent 2 weeks running detailed time and motion studies, photographing operations, interviewing crews, and calculating theoretical rates. He identified 173 discrete operations needed to assemble an M4. Under the current system, these averaged 9.7 hours each, totaling 456 hours spread over 19 days. His breakthrough insight was recognizing that most of those operations didn't actually require 19 days. They took 19 days because of waiting for prior steps, waiting for tools and components to arrive, waiting for inspectors, waiting for specialized crews to be free. The solution was to eliminate waiting by imposing continuous flow manufacturing. Instead of people going to static tanks, tanks would move past specialized workstations. Every station would have the tools and parts at hand. Workers would repeat the same operation over and over, gaining speed and accuracy. Inspection would be embedded and continuous, not batched. When he presented his proposal to Chrysler management and Army Ordnance representatives in August 1942, the reaction ranged from skeptical to hostile. Brig. Gen. James Wesson, Chief of Ordnance, stated flatly that tanks were not cars and could not be built like cars. Precision demands, complexity, and weight made continuous flow impossible. Chrysler's engineering staff agreed and documented a list of obstacles. 15-ton hulls were too heavy for standard conveyors. Turret installation required overhead cranes that couldn't operate above a moving line. Final drivetrain assembly involved components over a ton. Welded hulls demanded static positioning for proper penetration and cooling. Sorensen answered each point with specific countermeasures. Heavy-duty conveyors used in locomotive shops could handle 15 tons. Turrets could be installed by mobile gantry cranes synchronized with the line. Heavy subassemblies could be pre-positioned at specific stations with dedicated lifting gear. Hull welding could be completed at dedicated stations, where the line paused briefly before resuming flow. Arguments dragged through August and September. Army Ordnance cited regulations that mandated inspection protocols incompatible with a moving line. Chrysler feared the downtime and disruption of a massive reconfiguration. Sorensen finally played his trump card, a demonstration. He proposed to commandeer one corner of the plant, Section D, and build 3 tanks using continuous flow while the main floor continued with the traditional method. If his line could produce 3 tanks faster than the old method could produce 1, Chrysler and Ordnance would authorize full-scale implementation. The demonstration began on October 1, 1942. Sorensen's team had 3 weeks to design and install a prototype line in Section D, previously used for subassembly work. The challenge was huge. They needed custom conveyors for 15-ton loads, specialized tooling positioned for continuous access, material handling for components up to 2,000 pounds, and a synchronized workflow that matched every station's capacity. Sorensen brought experts from Ford's River Rouge plant. The the most advanced manufacturing facility in America. They designed hydraulic lifts for heavy components, roller conveyors with custom load-bearing capacity, overhead delivery for small parts and tools, and welding fixtures that clamped hulls in a perfect position. The prototype line stretched 180 feet with 11 primary stations, each designed to complete its work in exactly 12 minutes. Station 1 received raw hull components. Station 2 performed primary hull welds with dedicated fixtures. Station 3 installed internal structural members. Station 4 mounted the suspension and hull floor. Station 5 installed transmission and final drives. Station 6 set the engine and cooling system. Station 7 wired the electricals and instrumentation. Station 8 accepted a fully assembled turret from a parallel line and mated it to the hull. Station 9 fitted external components, fenders, tracks and inspectors and on-vehicle tools. Station 10 handled final systems integration and fluids. Station 11 performed operational testing and inspection. The first trial ran on October 23, and it was a mess. Conveyors jammed under hull weight. Weld fixtures didn't match real-world geometry. Crews trained in the old approach struggled with station-specific tasks. Timing went out of sync as stations finished at different rates. Army Ordnance observers, watching the chaos, declared the experiment a failure and urged Sorensen to stop and return to the proven method. Chrysler management, worried about wasted resources and ongoing delays, agreed. Sorensen refused. He had seen the same thing in 1913 when the Model T line first moved. Early failure doesn't prove impossibility. It reveals specific problems that demand specific fixes. He asked for 2 more weeks. The next 14 days were a blur of improvisation. Engineers reinforced conveyor supports with better load distribution. Weld fixtures were modified to match the actual hull geometry rather than the blueprint ideal. Workers were retrained intensively, not as general tank assemblers, but as experts in their station's operation. Cycle times were rebalanced by splitting or combining tasks. The second trial began on November 9. The improvement was dramatic but incomplete. Tanks moved down the line but paused often for on-the-fly problem solving. Total time for 3 tanks, 8 days. Better than the traditional method, but nowhere near Sorensen's promised 2 days. The breakthrough came on November 16 when Sorensen rolled out his most radical innovation, the moving crew. Instead of fixing workers at stations, small specialized teams walked with the hulls, performing their operation as the tank crept along. That eliminated station transfer delays while preserving continuous motion. The third trial kicked off on November 23, Thanksgiving week. Sorensen staked his reputation on this run. If it failed, Ordnance would shut the experiment and bar him from further involvement. The result exceeded his own projections. 3 complete Shermans, fully assembled, tested, and combat-ready, came off the prototype line in 41 hours, 17 hours per tank, versus 456 hours before, a 96.3% reduction in assembly time. More stunning, the quality matched or exceeded the traditionally built tanks. Inspections found no significant defects. Test drives showed every system performing correctly. Armor welds passed ultrasonic checks. The tanks were ready for war. Army Ordnance officers were stunned. Brig. Gen Wesson personally inspected all 3 vehicles. He found no evidence of rushed workmanship or compromised quality. He approved the immediate expansion of the system across Detroit tank arsenal. If you're into how American innovation turned the tide of war, hit subscribe and tap the bell. We bring you the overlooked engineering breakthroughs that changed history. Don't miss the next deep dive into wartime manufacturing miracles. Full-scale transition to continuous flow began on December 1, 1942. The task was extraordinary. The entire 1.6 million square foot factory floor had to be reconfigured. Traditional stations torn out, new lines installed, workers retrained, and supply systems redesigned, all while maintaining enough production to meet urgent military needs. Sorensen divided the plant into 4 parallel assembly lines, each capable of operating independently. That redundancy meant a mechanical issue on one line wouldn't halt output. It also let some lines keep building the old way while others are converted. Line A began continuous flow operations on January 7, 1943. Initial output was cautious, 1 tank every 8 hours. As crews gained experience and engineers tuned procedures, cycle time fell fast. By January 31, Line A was producing 1 tank every 4 hours, 6 a day. Line B was converted on February 15. Line C followed on March 1. Line D, the final line, started continuous flow on March 22. By April 1, all 4 lines were running, outputting 24 tanks per day, up from 3 per day just 4 months earlier. But Sorensen wasn't satisfied. His original math showed a 1-hour cycle was attainable. The 4-hour pace reflected only a partial implementation of true continuous flow. More refinements were needed. The main bottleneck was turret installation, which slowed the line with demanding precision. Sorensen's team designed a specialized turret mating station where hulls paused briefly while mechanically assisted arms lowered turrets with exceptional accuracy. The pause lasted 6 minutes, but eliminated what had been a 30-minute choke point. Engine installation posed a similar challenge. The Wright R975 radial weighed about 1,150 pounds and required precise alignment with transmission and cooling systems. Sorensen developed an automated engine dolly that carried engines alongside the moving hull, allowing the installation crew to work while the tank crept forward. Final drive installation, mounting the heavy transmission and differential, had relied on overhead cranes that couldn't effectively operate over a moving line. Sorensen's solution was mobile floor-mounted lifts that tracked with the hull, eliminating lift delays. These refinements rolled out through April and May 1943. By June 1, cycle time was down to 90 minutes per tank. June 30 hit 75 minutes. July 31 reached 63 minutes, just faster than 1 per hour. The transformation was complete. Detroit Tank Arsenal, which had produced 12 tanks in April 1942 using the traditional approach, built 721 in July 1943 with continuous flow, a 60-fold increase in 14 months. The statistical comparison was jaw-dropping. Traditional assembly consumed 456 man-hours per tank. Continuous flow consumed 48. Labor efficiency rose 950%. Factory space utilization improved 400% as moving lines enabled far denser workstation layouts. Material handling efficiency jumped 600% via automated delivery systems. Quality defects fell 73% despite the speed, as station specialists developed extraordinary proficiency. The impact rippled far beyond Warren. Sorensen's methods were rapidly adopted at other tank plants. Fisher Body Tank Arsenal in Grand Blanc, Michigan, converted to continuous flow in April 1943. Pacific Car and Foundry in Renton, Washington, followed in May. Federal Machine and Welder in Warren, Ohio, began conversion in June. By the end of 1943, American factories were producing 2,100 Shermans per month, up from about 200 in mid-1942. The increase flowed less from building new plants than from Sorensen's manufacturing revolution. The German reaction revealed the strategic shock. German intelligence had estimated U.S. tank capacity at roughly 300 units per month based on traditional methods. When actual output blew past 2,000 a month, German planning assumptions collapsed. Heinz Guderian wrote in his diary in November 1943, "Intelligence reports indicate American tank production has increased tenfold in a year. If correct, this represents an industrial capacity beyond our ability to counter. We cannot destroy tanks faster than they can replace them." Armaments Minister Albert Speer presented comparative figures to Hitler in December 1943. Germany, at its peak, was producing about 540 tanks per month. America was at 2,100. A 4-1 American advantage made a German victory in any prolonged war mathematically impossible. The strategic implications were profound. U.S. armored divisions in Europe could sustain operations knowing replacement tanks would arrive in weeks. Losses that crippled German panzer formations merely inconvenienced American units. The Sherman, criticized for inferior armor and firepower compared to Tigers and Panthers, won through crushing numerical superiority enabled by Sorensen's methods. The Normandy campaign made this decisive. From June 6 to August 31, 1944, U.S. forces landed roughly 2,100 Shermans in France. German forces destroyed about 800 in combat, but replacements arrived faster than losses accumulated. By September 1, American armored strength in France exceeded D-Day levels despite heavy fighting. German formations could not match this replacement tempo. The 2nd SS Panzer Division, Das Reich, landed in Normandy with 89 tanks and received 0 replacements during 3 months of combat. By September, it operated with 14 functioning tanks, effectively destroyed as an armored formation. The production advantage extended beyond tanks. Sherman output was so high that variants became feasible without compromising main battle tank supply. The M4A3E8 with the 76mm gun, the M7 Priest self-propelled howitzer, the M10 tank destroyer, and the M32 recovery vehicle all leveraged Sherman chassis components. That part's commonality was itself a product of Sorensen's mass production mindset. Sorensen's influence went beyond specific techniques. He demonstrated that military production could achieve the same industrial efficiencies once reserved for consumer goods. The Army Ordnance Corps, initially hostile to civilian manufacturing expertise, ultimately adopted continuous flow principles across weapons programs. Artillery shell production implemented assembly line methods, climbing from about 2 million monthly shells in early 1942 to 18 million per month by mid-1943. Aircraft engine production synchronized assembly. Wright Aeronautical hit 1,500 R975 engines per month compared to 150 with traditional methods. Small arms ammunition reached previously unimaginable levels, with Lake City Army Ammunition Plant producing 4 million rounds per day using continuous flow loading lines. The transformation validated Sorensen's core principle. Complexity does not preclude efficient production. It demands a different organization. Breaking complex assemblies into simple, repeatable operations allows workers to achieve extraordinary proficiency. Continuous flow eliminates waiting. Specialized tooling lowers skill barriers. Synchronized timing prevents bottlenecks. Proven on tanks, these principles became foundational to modern manufacturing. Post-war industrial production, from cars to electronics to construction equipment, made continuous flow standard practice. Sorensen's wartime innovations accelerated industrial evolution by decades. The human dimension mattered as much as the numbers. Detroit Tank Arsenal employed nearly 40,000 workers at its peak. Under the old methods, that workforce might have delivered 800 tanks a year. Under Sorensen, the same people built over 8,000, 10 times the labor productivity. It didn't come from harder work or longer hours. Continuous flow crews reported less physical strain than traditional assembly. The key was eliminating wasted effort, time spent hunting for tools, lugging heavy parts, waiting on prior steps, or repositioning for different tasks. Specialized stations meant every motion was productive. Worker satisfaction improved despite initial resistance. The lines delivered less fatiguing work at the same pay. The psychological reward of seeing complete tanks roll off the line in hours instead of weeks was real. Union leaders, skeptical at first, became advocates. The economic impact reshaped communities. Warren, Michigan, exploded from a rural township into an industrial city, growing from about 10,000 residents to 50,000 in 2 years. Housing, schools, hospitals, and infrastructure expanded to support tank workers. Similar booms followed other plants that adopted Sorensen's methods. Greater Detroit became the undisputed arsenal of democracy. Beyond tanks, the region turned out aircraft engines, military trucks, artillery shells, and countless other instruments of war. But tank production was the emblem of American industrial might. Sherman's rolling off assembly lines that Germans believed could never be harnessed to build tanks. Before we carry forward the legacy of this innovation, it's a perfect moment to subscribe if you haven't already. Hit that button and turn on notifications so you don't miss stories where individual brilliance changed the course of history. Your support helps us uncover forgotten engineering triumphs. Post-war analysis confirmed that Sorensen's manufacturing revolution was as militarily significant as any weapons development. A 1948 RAND study on industrial mobilization concluded that improvements in manufacturing efficiency contributed more to Allied victory than any single weapons technology. The study singled out tank production as the prime example of civilian industrial expertise, transforming military potential. In November 1945, Charles Sorensen received the Medal for Merit, the nation's highest civilian decoration. The citation read, "For exceptionally meritorious conduct in the performance of outstanding services to the United States in the field of industrial production." His revolutionary manufacturing techniques increased armored vehicle production tenfold, providing the material superiority decisive to Allied victory. Sorensen's post-war career underscored his lasting impact. In 1944, he became president of Willys-Overland Motors and applied continuous flow to civilian Jeep production. Later, as a consultant, he helped firms worldwide build modern production systems, spreading American manufacturing efficiency globally. His 1956 autobiography, My 40 Years with Ford, devoted 3 chapters to tank production, calling it his most satisfying professional achievement despite decades of automotive success. "Building the Model T taught me the principles of manufacturing," he wrote. "Building the Sherman proved those principles could win a war. I am proudest of the tanks, not because they were the better product. They were not, but because they were more important." The technical legacy of continuous flow tank production shaped military manufacturing through the Cold War and beyond. The M48 Patton, M60, and M1 Abrams all incorporated production methods descended from Sorensen's World War II innovations. Modern armored vehicle factories around the world use synchronized lines, specialized stations, and continuous flow. The M1 Abrams line at the Lima Army Tank Plant, successor to Lima Locomotive Works, which built early Shermans, produces roughly 1 tank every 2 weeks. Slower than Sorensen's hourly Shermans, yes, but reflective of vastly greater complexity. Adjusted for complexity, the Abrams line achieves efficiency comparable to wartime continuous flow. The strategic lesson, that manufacturing efficiency can yield overwhelming numerical superiority, remained relevant throughout the Cold War. U.S. military planning assumed that in any extended conventional conflict, superior production capacity would prove decisive. Validated by World War II experience, that assumption shaped procurement, force structure, and industrial preparedness. The Sherman itself had a remarkably long service life, proving that Sorensen's speed did not compromise quality. Sherman served on the front lines into the 1970s. The Israel Defense Forces fielded upgraded Shermans in the Six-Day War in 1967. Paraguay reportedly operated Shermans into 1997, more than 50 years after production. That longevity shows mass production and durability are not opposites. Properly designed products, built with efficient methods and precisely calibrated tools, can match or exceed the quality of traditionally crafted equipment. The Sherman's mechanical reliability, often overlooked amid debates about armor and firepower, owed much to production line consistency. Tanks built to identical specs, with consistent tolerances, delivered uniform performance. Sorensen's methods had profound economic implications. A Sherman cost roughly $50,000 in 1943, about $800,000 in today's dollars. German Panthers cost the equivalent of about $140,000 then. Sherman's lower cost stemmed less from simplicity than from manufacturing efficiency. That cost advantage let America deploy armor lavishly. Tank destroyer battalions, armored cavalry squadrons, and separate tank battalions all received Shermans in numbers that would have been economically impossible with more expensive vehicles. The Sherman became ubiquitous, serving in roles from frontline combat to headquarters security because America could afford to use them everywhere. Comparative production tells the story of armored warfare's outcome. In World War II, the United States built 49,324 Sherman tanks. Germany produced about 6,567 Panthers and 1,347 Tigers, roughly 8,000 medium and heavy tanks combined. The Soviet Union, using its own flavor of mass production, built 57,365 T-34s. U.S. production alone outstripped German output 6-1. Combined Allied production delivered a 16-1 numerical advantage. That crushing edge didn't come from superior designs. German tanks were often better on paper, but from superior manufacturing enabled by continuous flow. The human cost of that advantage is deep but hard to quantify. How many American soldiers lived because replacement tanks arrived quickly? How many battles were won by numbers instead of tactical brilliance? How many German soldiers died facing wave after wave of Shermans that their industry could not match? The counterfactuals are unknowable, but the overall impact is clear. Manufacturing efficiency saved Allied lives and cost Axis lives. Germany's effort to match American production failed despite significant industrial capacity. German 1944 tank output peaked at about 540 per month, impressive by many standards, but dwarfed by American output. The constraint wasn't German engineering prowess or worker skill, it was methodology. German tank production remained largely artisanal, small batches built with craftsman techniques. Tigers and Panthers demanded hand-fitting, individual adjustments, and extensive post-assembly mods. Quality was excellent. The pace was glacial. German plants never implemented continuous flow assembly for tanks, partly due to design complexity, but mostly due to doctrinal resistance from procurement officials who equated customization with quality. That philosophical divide, mass production versus artisanal crafting, determined the material balance of the war. America's willingness to standardize, simplify, and systematize enabled production rates that Germany couldn't approach. Sorensen's work proved that in total war, adequate equipment in overwhelming numbers beats superior equipment in limited numbers. The legacy stretches into modern manufacturing economics. Continuous flow, lean manufacturing, just-in-time delivery, and synchronized assembly all draw from the principles Sorensen applied to tanks. Today's auto plants, electronics lines, and consumer goods factories all use variations of techniques proven on wartime armor. The Toyota production system, developed in the 1950s and often hailed as revolutionary, openly acknowledged its debt to American wartime production. TPS architect Taiichi Ohno studied Ford's methods and examined World War II innovations. Kanban, synchronized workflow, and continuous improvement all reflect the principles demonstrated at Detroit Tank Arsenal. Manufacturing education uses World War II tank production as a case study in rapid industrial transformation. Business schools teach the Sorensen method, identify bottlenecks, eliminate waiting, synchronize operations, specialize labor, and optimize flow. Forged under the pressures of war, these principles remain the foundation of industrial efficiency. The story of Charles Sorensen and Sherman production embodies a uniquely American approach to warfare, industrial problem solving. While other nations focused on tactical brilliance or technological edge, America applied manufacturing efficiency to overwhelm enemies with material abundance. This wasn't crude quantity over quality. It was the sophisticated understanding that a sufficient quantity carries its own quality. The leap from 19 days to 60 minutes is one of the most dramatic improvements in manufacturing history. The 96.3% cut in assembly time didn't come from rushing or accepting lower quality. It came from organizing work intelligently, eliminating waste, and applying proven industrial principles to a new challenge. Sorensen's impossible play wasn't impossible at all. It required someone willing to challenge assumptions, experienced enough to recognize inefficiency, and credible enough to force change through institutional resistance. His background as Henry Ford's manufacturing savant gave him the expertise and the credibility. His commitment to winning the war gave him the will to push. Army ordnance officers who dismissed him at first became enthusiastic advocates. Brig. Gen. Wesson, who had declared continuous flow tank assembly impossible, wrote in his 1946 memoir, Charles Sorensen taught the Army that military necessity does not excuse manufacturing inefficiency. His methods proved that precision and speed are not opposites. We should have listened from the start. Chrysler, which had never built tanks before the war and initially resisted Sorensen's methods, emerged as the world's leading tank manufacturer. The company produced about 25,000 tanks during the war, more than any other facility. After the war, Chrysler's defense division became a major contractor, building M48 and M60 tanks with evolved versions of Sorensen's methods. Detroit Tank Arsenal operated through the Cold War, producing for every American armored conflict up to Desert Storm. The facility finally ceased tank production in 1996, 54 years after its first Sherman rolled out. The original 1.6 million square foot building, where Sorensen sparked his revolution, was eventually demolished, but photographs from its operating days show assembly lines clearly descended from the system designed in 1942. The people who built Shermans, many of whom had never worked in a factory before the war, including large numbers of women, proved that ordinary citizens can achieve extraordinary production with the right organization. Rossi the Riveter became the emblem of industrial mobilization, but the reality was broader. Millions of Americans, most with no manufacturing experience, learned to build tanks, aircraft, ships, and weapons in a matter of weeks at efficiencies that astonished the world. That democratization of manufacturing skill was revolutionary. The traditional industry relied on master craftsmen whose years of experience couldn't be quickly replicated. Sorensen's methods broke complex operations into simple, teachable tasks. In weeks, inexperienced workers could reach the proficiency that once required years under an apprenticeship. The social impact was profound. Women, African Americans, and other groups long excluded from skilled manufacturing found opportunity in the war industries. Discrimination persisted, but the urgent need for labor forced open doors shut in peacetime. These workers proved their capability, helping to erode barriers that began to crumble under wartime mobilization and continued to fall in the decades after. The economic transformation of communities around tank plants mirrored the broader mobilization. Warren's rise from rural township to industrial city echoed similar shifts nationwide. War production created jobs, built infrastructure, and established industrial capacity that underwrote post-war prosperity. The men and women who built tanks went on to build the cars, appliances, and consumer goods that defined the boom years. Charles Sorensen died in 1968 at age 87, having watched his principles become global standard practice. The New York Times obituary called him the man who taught America to build tanks, though his contribution reached well beyond armor to the fundamental transformation of industrial production. His papers, donated to the Detroit Public Library, include detailed documentation of the tank revolution, engineering drawings, production schedules, time and motion studies, and correspondence that preserve the story of how one person's expertise reshaped armored vehicle manufacturing. Industrial historians and manufacturing scholars still consult them as primary sources on a pivotal moment in industrial development. A complete assessment of Sorensen's contribution doesn't stop at the 96% cut in assembly time, stunning as it is. It must weigh the strategic impact of overwhelming American tank production. From 1942 to 1945, American factories built more tanks than all other combatants. That superiority provided the material foundation of Allied victory in Europe and the Pacific. Every Sherman that landed on European beaches, nosed through French hedgerows, broke German defenses, and raced toward Berlin carried Sorensen's invisible signature. The tankers inside, the infantry they supported, and the civilians they liberated all benefited from the manufacturing efficiency that made American armor ubiquitous. German soldiers facing endless waves of Shermans, destroying one only to meet three more, understood they weren't just fighting American armor. They were fighting American industrial capacity. The Wehrmacht's tactical excellence, its superb tank designs, and its experienced crews all proved inadequate against a foe that replaced losses faster than they could inflict them. In the final analysis, Sorensen's 90% cut in tank build time wasn't about speed for its own sake. It was about turning industrial capacity into military power. It was proof that free market capitalism and democratic organization could outproduce authoritarian command economies. It was American ingenuity applied to manufacturing to achieve results that seemed impossible by traditional standards. The leap from 19 days to 60 minutes stands as a testament to what determined innovation can accomplish. A civilian armed with expertise and resolve revolutionized military manufacturing. His methods supplied the means of victory. His legacy shaped industrial production for generations. The Shermans built under Sorensen's system weren't the best tanks of World War II, but they were good enough, reliable enough, and present in such overwhelming numbers that they crushed the Wehrmacht under American steel. That combination, adequate quality and overwhelming quantity, proved the decisive formula of industrial warfare. It's the formula Sorensen perfected on the floor of Detroit Tank Arsenal when he made the impossible possible and cut tank build time by 90%. Today, when manufacturing experts discuss continuous flow, lean, or synchronized assembly, they're applying principles proven in wartime tank production. When military planners think about industrial mobilization, they estimate capacity through the lens of lessons learned on Sherman lines. When historians ask why the Allies won, they place increasing emphasis on material superiority enabled by manufacturing efficiency. And when we tally decisive contributors, Charles Sorensen deserves a place alongside generals and scientists. His battlefield was the factory floor. His weapons were conveyors and specialized tools. His victories were measured in tanks per hour instead of miles captured. But his contribution to winning the war was as vital as any campaign. The man who made the impossible possible, the one who cut tank build time from 19 days to 60 minutes, taught America how to bury its enemies under an avalanche of armor. He proved that sometimes the most important military innovations happen not on the battlefield, but in the factory. In modern war, the assembly line can be as decisive as the front.